July 5th, 1943. Operation Citadel is underway on the dusty plains of Kursk. The Third Reich unleashes its ultimate weapon, the Panzerkampfwagen 5 Panther. It was designed to completely obliterate the Soviet T-34 tank and reclaim dominance on the Eastern Front. The German High Command spent a staggering 117,100 Reichsmarks on each of these 45-ton beasts, eventually building over 6,000 units. Yet, during the opening days of the largest tank battle in human history, the reality was far from the propaganda. Instead of sweeping the enemy away, over 160 Panthers were rapidly knocked out of action. Many were not pierced by Soviet artillery, nor were they ambushed by anti-tank infantry. Instead, they spontaneously combusted, burning into charred husks on the side of the dirt roads. Welcome back to DEFUNCT. Today, we are going to perform a complete digital autopsy on the Panther tank. We will expose the catastrophic mechanical failures that turned the pride of the Wehrmacht into a self-igniting death trap, initiate the 3D rendering sequence, and let us strip away the outer layer of Zimmerit anti-magnetic paste and the standard camouflage paint. On paper, this machine is an absolute masterpiece of ballistic engineering. Isolate the main armament in the turret. What you are looking at is the 75mm KWK 42L70 rifled gun. By elongating the barrel to exactly 70 calibers, German engineers achieved a terrifying muzzle velocity of 1,120 meters per second when firing specialized tungsten core ammunition. To put that into perspective, that is roughly 3 times the speed of sound. At a distance of 1,000 meters, this armor-piercing projectile could easily punch through 149 millimeters of angled steel armor. It is the physical equivalent of driving a high-speed tungsten spike through a solid concrete vault door. But a tank is not just a stationary cannon. It requires mobility, and that is where the mechanical nightmare begins. Let us pan the camera to the rear of the chassis and make the 40mm thick rear armor plating completely transparent. We are going to dive straight into the beating heart of this 45-ton Titan. Housed within this incredibly cramped space is the Maybach HL230 P30 engine. Execute a horizontal cross-section cut right through the middle of the engine block. This is a massive 23-liter, naturally aspirated V12 engine, capable of generating 700 horsepower at 3,000 revolutions per minute. In a vacuum, this is a magnificent piece of engineering. However, physics dictates a harsh reality when it comes to power-to-weight ratios. The Panther was originally conceptualized as a 30-ton medium tank, but thanks to the addition of heavier sloped frontal armor, its total combat weight ballooned to a massive 45 tons. This meant the Maybach 512 was constantly redlining, desperately struggling to drag a mountain of steel through the thick Russian mud. It is the mechanical equivalent of forcing a standard pickup truck engine to pull a fully loaded commercial freight train up a steep incline. The sheer amount of mechanical stress placed on the crankshaft and pistons was astronomical, generating a tremendous amount of internal friction and consequently, heat. Now let us analyze the catastrophic flaw in the Panther's thermodynamic design. Zoom in on the walls surrounding the engine. Notice how tightly sealed the entire compartment is. German engineers designed the initial Panther models with a watertight engine bay. They wanted the tank to have deep wading capabilities, allowing it to cross rivers completely submerged. While this sounds brilliant in a briefing room, it created a fatal thermodynamic trap. on the battlefield. Without adequate airflow, this watertight compartment effectively became a sealed convection oven. The immense heat generated by the overworking 700 horsepower V12 had nowhere to escape. The ambient temperature inside this enclosed metal box would rapidly skyrocket, exceeding the operational limits of the surrounding components. Let us look closer at the air intake system. In the dusty environment of the Russian steppes, the Panther's engine required massive amounts of clean oxygen to maintain combustion. However, the air filters were woefully inadequate for the dense, abrasive dust clouds kicked up by a marching armored column. As these filters became choked with particulate matter, the engine began to suffocate. The EFR's air-to-fuel ratio became dangerously rich, meaning too much fuel was being pumped into the cylinders without enough oxygen to burn it completely. This unburned fuel would wash the lubricating oil off the cylinder walls, increasing friction exponentially and driving the internal temperature even higher. It was a vicious cycle of thermodynamic self-destruction. Focus the macro probe lens on the intricate network of fuel lines and the 4 twin-choke Solex carburetors mounted right on top of the engine block. Under normal conditions, these components are designed to efficiently mix liquid gasoline with air. However, as the temperature inside the sealed compartment reached critical levels, a dangerous phenomenon known as thermal expansion began to take effect. The immense heat caused the rubber gaskets, seals, and flexible fuel lines to warp, degrade, and eventually crack. Gasoline is a highly volatile fluid, and now it was no longer contained. Raw, unburnt fuel began to leak directly out of the compromised carburetors and cracked lines, pooling at the bottom of the engine bay. But the leak itself was not the ignition source. To understand the true catalyst of the Kursk disaster, we must look at what this raw fuel was dripping onto. Shift the thermal imaging overlay onto the dual exhaust manifolds bolted to the sides of the V12 block. Because the engine was constantly running at maximum capacity just to move the 45-ton chassis, these exhaust pipes were literally glowing red hot. The combination was mathematically lethal. You have a highly pressurized, completely enclosed metal box devoid of cooling airflow. You have raw gasoline leaking from degraded rubber seals, and you have red-hot iron exhaust pipes acting as a constant ignition source. It was no longer a question of if the tank would catch fire, but exactly when the spontaneous combustion would occur. The Panther was fundamentally designed as a ticking thermal time bomb, destroying its own engine before a single Soviet tank even came into visual range. But the inferno in the engine bay was only half of the mechanical disaster. To fully comprehend the sheer scale of the Panther's engineering failure, we must tear down the tracks and dissect the transmission. Initiate the structural separation protocol and detach the massive interleaved road wheels and the wide combat tracks from the lower chassis. We are moving our digital probe from the rear engine compartment to the frontal drive sprockets. Strip away the heavy 85mm sloped frontal armor plate. What you are currently looking at is the ZFAK 7200 Synchromesh gearbox and the final drive housing. In a front-wheel drive tank configuration, the immense rotational energy generated by the Maybach 5, 12 in the rear, must travel through a long drive shaft. This shaft traverses the entire length of the fighting compartment, only to be processed and distributed by this forward transmission. Execute a close-up isolation on the final drive gear clusters. This is where German engineering hubris met the unforgiving laws of metallurgy. to rotate a 45-ton steel behemoth through deep mud, you need to transfer an astronomical amount of torque. Standard heavy machinery logic dictates the use of a planetary gear system. This design distributes the mechanical load across multiple interlocking cogwheels, significantly reducing the stress on any single point. But the Panther did not use planetary gears. Instead, German designers utilized a dual spur gear system. This meant that the entire kinetic resistance of the 45-ton tank was concentrated onto a single point of contact between two straight-cut gear teeth. It is the mechanical equivalent of trying to halt a rolling freight train by wedging a single glass rod into its iron wheels. Now, let us factor in the metallurgical crisis of 1943. Due to relentless Allied blockades, the Third Reich was severely starved of critical alloying elements like molybdenum, tungsten, and nickel. These are the exact elements required to forge high-tensile, shatter-resistant steel. Without them, the gears inside the Panther's final drive were surface-hardened, but internally brittle. Let us run a 3D physics simulation of a real-world scenario at the Battle of Kursk. The Panther is sunk half a meter deep in thick, heavy Russian mud. The driver engages the clutch and floors the accelerator. The Maybach engine screams to 3,000 revolutions per minute, sending a violent spike of 700 horsepower down the central shaft. As the clutch connects, the immense kinetic force slams into the brittle spur gears of the final drive. At the exact same time, the dense mud exerts a massive counter-rotational drag on the tracks. Activate the shear stress overlay on the screen. The physical tolerance of the low-carbon steel is instantly exceeded. In a fraction of a second, the gear teeth violently snap off. Switch to a high-speed macro internal view. The shattered metal shards do not just disappear, they become deadly projectiles trapped inside the sealed transmission housing. As the remaining gears continue to rotate, these hardened steel fragments are crushed between them, acting like an industrial shredder. The transmission violently locks up, generating a massive shower of physical sparks and an excruciating screech of tearing metal. The Panther is now completely paralyzed on the battlefield. But this frontal mechanical disaster is about to trigger a fatal chain reaction in the rear. With the transmission suddenly jammed, the tracks refuse to move. The panicked driver, desperate to escape the artillery kill zone, instinctively presses the throttle harder. He is attempting to force the tank forward by sheer engine power. This causes the already suffocating Maybach HL230 to over-rev disastrously. We are now returning to the sealed, watertight engine bay we analyzed in Part 1. The internal temperature breaches the absolute critical threshold. The extreme thermal expansion warps the fuel pump housings beyond their physical limits. The degraded rubber gaskets completely disintegrate. Initiate the fluid dynamics particle simulation. The internal fuel system, operating under a pressure of 1.5 atmospheres, now becomes a flamethrower pointed at its own heart. Highly volatile 74-octane synthetic motor fuel begins spraying in a high-pressure mist directly from the ruptured Solex carburetors. Gravity pulls this raw fuel downward, pooling exactly where the dual cast iron exhaust manifolds are radiating heat at over 800 degrees Celsius. The flash point of standard synthetic gasoline is roughly 45 degrees Celsius. The mathematical outcome is inescapable. The exact moment the vaporized fuel touches the glowing iron, spontaneous combustion occurs. A violent fireball erupts inside the confined space. Because the engine bay was designed to be watertight for deep river wading, it is completely sealed off from the outside atmosphere. This traps the rapidly expanding gases and flames, effectively becoming a pressurized blast furnace. The internal fire extinguishers, triggered by bimetallic heat sensors, deploy their chemical suppression gas. But they are instantly overwhelmed by the sheer volume of continuously pumping fuel. The flames rapidly consume the rubber fan belts, melt the electrical wiring harnesses, and begin scorching the 20mm steel firewall. This wall is the only thing separating the screaming V-12 from the trapped crew compartment. Re-engage the outer armor shell and pull the camera back to a sweeping wide shot of the Kursk steppes. On paper, the Panzerkampfwagen 5 Panther was an undisputed technological marvel. Its 55-degree sloped frontal armor could effortlessly bounce the 76mm BR-350A armor-piercing shells fired by the Soviet T-34s. Its high-velocity 75mm cannon could destroy enemy armor from beyond visual range, acting as the ultimate sniper of the battlefield. But weapons of war are not fought on blueprints. They are bound by the unforgiving laws of physics, thermodynamics, and material science. By marrying a brilliant ballistic platform to a fatally compromised mechanical foundation, the Third Reich created a 117,100 Reichsmark paradox. Dozens of these majestic steel beasts burned themselves to the ground on their very first days of combat. Their lethal cannons were rendered utterly useless because their internal organs tore themselves apart under their own weight. They were the ultimate asymmetric monsters, invincible from the outside, but fatally fragile from within. If you found this digital autopsy fascinating, do not forget to subscribe to DEFUNCT. Leave a comment below on which historical machine we should tear apart next. The most fatal flaws are always hiding beneath the heaviest armor.